This episode is sponsored by Fabulous, an app that helps you form healthy habits that stick. Click the link in the description to get a free 1-week trial and 25% off a Fabulous subscription. While it was not the first probe sent on a trajectory out of our solar system, Voyager 1 was traveling fast enough that it became the most distant object forged by human hands back in 1998. And although its primary mission ended even before that, it's still capable of doing a little science and sending some messages home. And this week in Nature Astronomy, astronomers reported a new way for Voyager 1 to give us access to interstellar space. Our sun doesn't just throw out light for all of the universe to see, it's also constantly emitting streams of charged particles, which astronomers call the solar wind. The solar wind forms a kind of messed up bubble called the heliosphere. The edge can be defined based on changes in the solar wind's speed, temperature, and density as it interacts with interstellar wind coming from everywhere else. Back in 2012, Voyager 1 crossed the boundary of the heliosphere that marks the bubble's outer edge. It was the first scientific instrument to swim through the stuff of interstellar space. And now, after spending 4 decades traversing the harsh environment of outer space and only operating on the power needed to toast your morning bagel, our little spacecraft keeps chugging along. Some of its instruments still take measurements, and we can still talk to it, though it takes over 21 hours to send a message one way. One phenomenon Voyager 1 can detect is known as a plasma oscillation event, or POE. These are basically waves of charged particles between the stars, the interstellar plasma, and they allow scientists to measure the plasma's density. Up until now, POEs appeared to be all shock waves created by something emanating from our heliosphere, like violent ejections of matter our sun spits out called coronal mass ejections. But this new research reports that for the 1.5 billion kilometers it's traveled since 2017, Voyager 1 has also been picking up a new kind of POE. They're weaker, but they're also much more constant, and they exist in between the usual shockwave-generated ones. It's unclear what their source is, but it may include a type of noise that other spacecraft have picked up during their missions much closer to home, caused by a plasma's electrons buzzing around and generating a small electric field. Wherever they come from, this new type of POE marks a whole new way for astronomers to use the Voyager probes to measure the interstellar plasma density. Instead of having to wait for a sudden shockwave to generate those random stronger POEs, we can get mostly continuous data, which overall will hopefully paint a more accurate picture of what it's like out there, where you, nor I, nor any living person will almost certainly ever get to go. Meanwhile, closer to home, we're getting more clues to how life on Earth came to be. In a paper published in this week's issue of Nature Geoscience, researchers suggest that the formation of a life-bearing planet is all about getting the timing right. Planets begin as giant clouds of gas and dust, with some of that material collapsing down into a bunch of small rocky bodies called protoplanets. Protoplanets then go on to smash into each other and gobble up smaller bodies until they become planet-sized. All of this collapsing and colliding generates so much heat that the protoplanet then melts. And that molten ball is made up of different elements, so the denser ones start sinking toward the core and the lighter ones rise up. This process is known as differentiation, and it's why the Earth is like an onion or an ogre. It's made of different layers. There's a crust where lighter silicate-based rocks dominate, and then a mantle made out of denser materials, and then an inner and outer core mostly made of metal. And we know that the other rocky planets in our solar system have layers as well. But one team of scientists wondered how much of a role differentiation may have played in the evolution of life. So they looked at the element nitrogen, which conveniently is both easy to track and acts a lot like other important substances that have a tendency to vaporize. Plus, nitrogen is essential for life all on its own. It's not just the most abundant gas in our air. Nitrogen atoms are a fundamental ingredient in DNA and other molecules that we need to not be dead. So this is really cool. They modeled planet making by taking a blend of nitrogen-bearing metals and silicate powder and then compressing it up to 30,000 times the pressure of Earth's air at sea level. At that pressure, that mixture melted, and when everything cooled down, they had a bunch of tiny metal globs amidst a sea of glass. And each metal glob was like a tiny planet core. Based on the distribution of nitrogen in their samples, they concluded that if a protoplanet doesn't accumulate enough mass before it finishes differentiating, it'll lose a lot of its nitrogen to outer space. Which means that when a bunch of those depleted protoplanets come together to form a full actual planet, there won't be enough nitrogen left over to form life, at least not life as we know it. To provide the amount of nitrogen we see on Earth, its constituent protoplanets would have to have reached Moon or Mars sizes within 1 million or 2 years of the solar system forming. By growing that fast before differentiation finished, some of the nitrogen would stay dissolved in their cores. That nitrogen could then leak up, but not away inside a baby Earth. In the process, it would provide our planet with one of the many ingredients it used to make you and me and trees and anglerfish. This research offers an explanation for why some small rocky bodies don't have a lot of nitrogen, or other elements like carbon that vaporize in a similar way. It was not that the location in space didn't have any of those elements. It was that most of what they started out with probably leaked away. And it also means that Earth didn't form from some depleted space rocks and then get an influx of nitrogen from some other source later in its formation, as long as the protoplanet seeds it started from grew big enough, fast enough. So although this is a big claim, and there's more research still to be done, we might be one step closer to understanding how we and all of the other life on Earth came to be. And you can add pondering how the Earth came to be as part of your daily routine with our sponsor, Fabulous. Fabulous is a self-care and habit-forming app with over 20 million users. It was developed at Duke University and uses behavioral research to help support your goals. Like focusing on deep work or anything else that might suit your needs, the app is fully customizable, so it's really up to you. The first 100 people who click on the link in the description will get a free week trial and 25% off a Fabulous subscription, which also helps us, so thank you.